Hello everyone, I'm Chin Sao, a PhD student from Stony Brook University. Thanks for coming to my talk. I'm happy to present my work, IrEne, Interpretable Energy Prediction for Transformers. This is a joint work with Yash Kumala, Harsh Trivedi, Aruna Balasubramanian, and Niranjan Balasubramanian. As you all know, NLP models are becoming very effective for many tasks, but they're also becoming significantly larger. The problem is that training models can take days using hundreds of GPUs, which is very expensive. For example, one recent paper has shown that research and development of a transformer model can take $100,000 for computing resources, and it can cost nearly $10,000 for electricity. It is critical to study the energy consumption, especially when choosing and training large-scale NLP models. For example, if we know the amount of energy different models consume, we can prioritize which models to train first, and which models are better to deploy on the battery-powered mobile devices. Another key use case is that by analyzing energy bottlenecks, we can design more energy-efficient model architectures. So how do the community measure energy currently? Two recent papers measure the total amount of energy of a program by first reading the power counter values from hardware components, and then combine them based on the resource utilization. So this approach is easy to use and only requires software setup with no additional effort. However, previous research has shown that reading values from power counters without any calibration is inaccurate. So this figure shows an example of the GPU power timeline when running a compute-intensive program. The program instantaneously starts at T1 and then stops at T2, which should be reflected in the mirror power. However, instead, there's a lag in this mirror power represented by the blue timeline. So it increases gradually after the program starts and decreases gradually after the program ends. This is inaccurate. Another problem is that energy is not always linear relative to the hardware utilization, because non-utilization behaviors also cost energy. For example, this figure shows the GPU architecture. The energy consumed by the streaming multiprocessor to perform the computation does correlate to utilization, but the hardware community found the energy bottleneck for GPU is the data movement in the GPU memories instead of the compute processors. So GPU utilization alone cannot reflect such kind of consumed energy. Now let's do a quick recap of the problems. We know that using uncalibrated power values alone cannot reflect hardware energy activities. We also know that combining energy based on utilization alone cannot reflect non-utilization energy behaviors. More importantly, only knowing the total amount of energy of a model cannot provide analysis of the energy inside this model. So to solve these problems, we designed a system called IrEne. The idea is to build a learning-based energy estimator to accurately predict energy of NLP models. We trained the energy estimator using the ground truth data collected by the hardware power monitor. So this way, the energy estimation is still easy to use and can provide more accurate measurements. So to do this, we view the power value as features and also include other hardware resource features like the GPU clock frequency to reflect the energy activity. Moreover, we also use the model information, which allows us to learn how to combine the energy consumed by each of these model parts. Importantly, this model information also allows us to provide interpretable analysis of the energy inside this model. So to provide this kind of interpretable energy estimation, we need to first build a proper abstraction for the models. From a computational point of view, a model from the bottom level consists of a set of math operations, like addition, multiplication, or subtraction. Then these basic math operations can be grouped into higher-level machine learning operations, like linear layer or softmax layer. These ML-level operations are model-agnostic primitives are used across different models. And then these ML-level operations can be further grouped into module-level operations. So these are the groups of lower ML-level nodes operations that reflect the logical units of the NLP algorithm defined the model authors. For example, the attention module is basically a different combination of the linear layer and softmax layers. By arranging different modules together, we can form an end-to-end model. So our focus in this paper is the ML level and module level operations. The operations at each level are grouped into a tree manner. So here I want to show you one example, which is the one-layer BERT model. As you can see, at the bottom part, the ML level operations are shown in the orange boxes, like linear or layer long. And then at the module level, operations is just a group of the ML level children nodes, as shown in these blue ovals. So BERT self-attention is basically a different combination of linear and matrix multiplications. One thing I want to say that the root node is the entire model. So with this model tree abstraction, we formally state the problem of interpretable energy prediction as follows. So given the model specification, the goal is to predict energy for every model node in this model tree. To achieve this goal, we need to first create a training dataset. So we run each operation with different input data, and then use an external power monitor to collect the ground truth energy for each node in this model tree. So our solution for this interpretable energy estimation is the IrEne system. So IrEne works by taking the model specification, basically the model PyTorch code or model input information as the input. And then we will use a tool called JITTrees to build this model tree structure. And then extract the model-specific features, such as input information like batch size, input sequence length, and also the amount of computation like flops, and the amount of data movement in the GPU. So these are model static features. Then we run this model on a given hardware device, profile the CPU, GPU memory, resource features, and clock frequency, etc. So these are hardware-dependent features and also the model-dependent. Then we fed both sets of features into a multi-level linear regression predictor to estimate the energy for each node of this model tree. Recall that in IrEne, we define two sets of nodes in a model tree, ML-level operations and module-level operations. So this multi-level energy predictor works as follows. We first build specialized predictors for each kind of machine-level operations. And then we are building one type of module-level general predictor, which takes the features from the children nodes and predict the energy. So this type of features are the same for both the ML and the module-level operations, which make it generalizable. Now I'd like to go a little deeper on how we design the two sets of energy predictor. So the ML-level energy predictor takes the tensor data as inputs and then output the predict energy. We found using a simple linear regressor works well, which basically takes the features and learn a weighted combination of them. So we build specialized predictors for each type of the machine learning operations. These predictors are still generalizable because all models are using these basic operations. In our paper, we also discuss how we could support customized ML-level operations. Now for the module-level energy predictor, the idea is to aggregate the predict energy from the children nodes. We found that simple summation wouldn't work. Instead, we learn a weighted combination of this predict energy from the children nodes. Well, remember that this module-level predictor is a general or generic energy predictor for all the modules, which make it generalizable even to other new unseen models. So to supervise this model, we scale the mean square error with ground truth energy, since the scales of energy at different levels of the trees are very different. And then we train it in an end-to-end fashion, since the error signal in the energy prediction of any node can back-propagate through the whole subtree. Now to evaluate the systems, we use two desktop PCs, each with two GPUs, and we use the open energy monitor for collecting the energy ground truth. We define the energy error as the deviation percentage between the predict energy and ground truth energy. We evaluate two sets of systems. One is the state-of-the-art baseline, called the experiment impact tracker, and then we use our IrEne system, we specifically use leave one out cross validation to compute the errors. So we evaluate 6 different transformer models, and then we collect the ground truth energy for different levels of operations. So this table below shows 3 models, shows the statistics for 3 such models. I'm going to show the results for one machine. So our energy predictor is pretty accurate and gives only less than 7% energy error, which is much lower than existing models, which gives you more than 50% errors for all the transformer models. So there are similar results for other machines. In our paper, we have more results for ML level and module level errors. So now, since once we have this IrEne system, we can use it to find the energy bottlenecks. For example, we found that the energy bottleneck for a robotic-based model is actually the self-attention, but for the bird-based model is the output transformation that consumes the most energy. So to summarize, we design a multi-level energy predictor to accurately estimate the inference energy of transformers. IrEne also provides interpretable energy analysis for the blocks inside transformer models. Importantly, IrEne is extensible and generalizable to unseen transformer models. Thank you.